Hi guys, so for our first video today we're going to talk about the definition of a derivative. So our first unit is on derivatives, and today we're just going to preview this definition of a derivative. Specifically, we're going to talk about how we're going to find derivatives by or using the definition with polynomial functions only, and then we'll move on to look at more complicated functions. So to warm up and kind of get our gears moving into math, we're going to talk about a simpler function. So I'm going to give you this function, 2x minus 3. And my first question is, what's the slope of this function? Now, this is a really easy question. We should be able to see that our slope is 2. This is a linear function. It's in the form of y equals mx plus b, so obviously our slope that we see here is 2. But more importantly than what is the slope of this function, let's ask the question, what is slope? We throw around that word slope a lot. We talk about it in a lot of algebra classes, and we have a lot of different definitions of what we think it is and how we describe it. So to get our brains moving, how can we describe what slope is? So you might be thinking, well, I know that slope is some sort of rate of change. And definitely, you're right, it's some sort of rate of change. Specifically, we can describe slope as the change of y with respect to x. So for every unit change in x, y increases or decreases this much. We can talk about being rise over run. We can talk about it being what we call, m in an Algebra 1 class as delta y over delta x. That's a possibility. We have a slope formula for m as y2 minus y1 over x2 minus x1. And we can keep going. We could talk about different ways that we would describe slope, and we could come up with any number of ways. But if we kind of think about what that means, is that it's a specific change of y with respect to x, or a rate of change, or this change in y over change in x, that kind of idea. In this function of 2x minus 3, we can say the slope is 2, and specifically that slope is 2 at any point on that function. That's what makes it linear, is that change is constant. So if I change that function from a linear function of 2x minus 3, so let's call that number 1, if I change that function to f of x or y equals x squared, and I ask you what's the slope, now your answer is a little bit muddled. We can't actually answer that question of what's the slope because it's not something that is a constant rate of change. It's not something that has this change of y with respect to x as a constant, say 2 or 5 or negative 5. This function changes, and we can see that like in our function above. We can see obviously that it's this constant change because every unit x that we go over, we go up the same amount of spaces. And we can see that happening everywhere, but of course in a curve like x squared, that's not the case. If I go over 1 unit change from our x, that y value is shifting by a different amount every time. And so that's what makes it, not a constant rate of change. So if I ask you what the slope is, we can't really answer that question, but I should be able to ask the question, what's the slope at a given point? Because we can all agree that at the point, say, x equals 3, this is going to be an exaggerated graph. I'm going to put x equals 3 down here for a reason. So if I say that, say, x equals 3 at that point, I do know that the graph is changing, so I should still be able to come up with some rate of change at that particular point. But to actually find that becomes a little bit more challenging. The actual process for that is a little bit trickier. So instead of coming up with the exact form, because even if you do know how to do this and you know a lot of derivatives, which you should a little bit at least because you talked about it a little bit in pre-calc, let's talk about how we could maybe come up with an approximation for how that's changing. So one way to get an approximation for how that's changing is to approximate it with our slope formula. So let's approximate it with 2 points. We all agree that finding slope, I can use 2 points in this y2 minus y1 over x2 minus x1, this delta y over delta x. So if I pick another point, say this is at x equals 3, I'm going to, again, this is not to scale, but I'm going to pick a point up here, and we'll call that x equals 4. So my first point I'm going to use as 3, and then I'll evaluate into the function, so that should be 3, 9. This second point I'm going to use as 4, x equals 4, and again, if I evaluate that into the function, I get 16. Now connecting those, not the best. But here would be like a line that goes to those 2 points. And you can see it kind of hugs that curve nicely, and this rate of change that I'm seeing at that particular point, we can draw what's called a tangent line, so we can see and extrapolate how that thing is changing, and we can see it's moving up, and it's moving up at this rate, and it looks pretty darn close to the line that we already drew. If I actually find the slope between those 2 points, I end up getting 7. And again, like, we can maybe see that that's reasonable, but I just picked that point x equals 4, so let's pick a different point. If I wanted to come up with a better approximation than just 3, x equals 3 and x equals 4, if I want to come up with a better approximation for the slope at x equals 3, what do? Well, I probably should pick a point that's closer to 3 than 4 was. 4 was just the next point over, the next discrete point over, but I could maybe pick like 3.5. So we would have to evaluate that into the original function. So we'd put in x equals 3.5. We'd have to square it to get our y value. And just so we can kind of get the hang of it, I'm going to rewrite 9 also as 3 squared. And you'll see why here in a little bit of like why I'm actually writing it that way. But I can find the slope between those 2 points too. And again, that point here, if I draw in the line, that might be even a better function, a better approximation. I can see that that hugs the curve even better than that x equals 4. And again, my line might be a little bit better if I zoomed in really close and I could see that. But if I evaluate that with 3.5, and I put that into my calculator, I get a slope of 6.5. So again, I just picked 3.5. I said, that one looks better, but if I wanted to get even closer, maybe I could approximate it with something even closer than that. Maybe I would say use 3.1. So that's something that's really darn close, and I draw a line that goes through it, and it pretty much is that curve if I continue on, and I could use 3.01 or 3.001, but if I use, say, 3.1 to get a better approximation, and I evaluate this into my calculator, I get 6.1. So again, extrapolating, if I use 3.001 and 3.0000001 to approximate my slope, we can see that this thing here is approaching a value, and that value is 6. So it's safe to say the slope is 6 at that point. Now it's weird, right? Like, we took a curve and we just used approximations to get that. But that idea of using these approximations and getting closer and closer and closer to that exact point, because we can't actually find the slope at that exact point with the slope for, like, with the ideas of slope that we know right now, that idea of doing that is called a derivative. So that leads us to what the definition of a derivative is. Now, the definition of a derivative, notationally speaking, we write derivative as f prime. So we're going to define the derivative as f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Now, this might look a little bit complicated. This might look like math that we haven't actually talked about before, but this really is slope. And what we can see here of why it is slope, and you might have seen this again in pre-calc, you might have seen this h written as delta x, but same thing. So what is happening here is that we're taking this function, we're subtracting we're taking this function that's a little bit more than the x value, say, that we're approximating. So for any given value x, we're going to find the slope, but we're going to use a value that's kind of close to that, a little bit more than that, which is what we did here. We used 3, and then we found a value that's a little bit more than that. We used 3.1. So this would be like x plus 0.1, or 3 plus 0.1. And we subtracted off the function value again at that point, so that's where this is. This is that function value evaluated at a little bit more than the x value. This is the function evaluated at the x value in question. And in the denominator here, we have this change in x, which this change in x really is that h value that is represented. Now, we could write the denominator instead as h as x plus h minus x, just so that we can actually see that change in x, or delta x. But the x's would cancel and we'd be left with h. Now this limit, what this does is this makes that value that we're looking at the difference between that x value and the value that we're approximating it with, make that really, really, really small. In other words, instead of using 0.1, we're going to get really close to 0, so we're going to use 0.0001 and 0.00001, and what we want is something that's essentially 0. So although this might look complicated, this is exactly derived from what the slope formula is, which is why we started talking about slope. So in calculus, every time we talk about slope, we should be thinking derivative at that point. So if I was asking you to use the definition, and right now we know that the slope of y equals x squared. We know that the slope at x equals 3. We know the answer here is 6, and you might have known that anyway from different rules and shortcuts that you've learned in pre-calc, but we're not going to learn about or think about those right now. If I asked you to find what the slope is at x equals 3, and I asked you to use the definition to do that, let's start with then the definition of a derivative. Which again we just defined as a, for lack of a better term, derivative of the slope. So coming from and derived from that. Our function that we have in question here is x squared. So if I was finding the function at x plus h, I would evaluate the function at x plus h. So I would get x plus h quantity squared minus our function f of x, which is just x squared, over h. Now here's a problem. When I'm talking about limits, in general what we want to do when we talk about limits is we want to evaluate the function that we have, or evaluate the limit at the point that we're approaching. So if I evaluate this thing at 0, I have an issue because I have a divide by 0. I have a denominator error. So I can't actually evaluate it right now, but what I can do is potentially simplify this a little bit so that I can evaluate later. So if I simplify, say, the numerator, I can expand that out and make that look a little bit better. So that would be x squared plus 2xh plus h squared, if I expand out that binomial, minus x squared over h. And as I can see in the numerator, my x squared terms will end up canceling. And I'll also have an h here in the numerator that I can factor out from the denominator, because still, again, that denominator is the problem. I have a divide by 0. So let me rewrite that so we can see that a little bit better. If I have this in the numerator and this in the denominator, again, I can't plug in 0 yet, but I can factor out an h or cancel out an h from every term in the numerator with the denominator. And what's left then is 2x plus h. Now if I evaluate at h equals 0 and plug that in here, I don't have an issue. I don't have a 0 in the denominator anymore, so I'm good to go. I can evaluate and then I get 2x. So what we actually asked to find is, or what we found here is f prime of x is 2x, which means that when we are finding the slope at 3, so notationally we're saying we're finding the derivative at this value of x equals 3. If I use the function that I found for my derivative and evaluate at x equals 3, I get 6. So exactly what we thought, but this is actually proving that and showing that function. Now what's cool about the derivative of a of a curve is that this function here gives us the derivative at any point of x. It's pretty powerful. In a linear function, we know that the slope, or we know the derivative at any point of x is the same, and this is not quite the same. Obviously, it's changing, it's varying, but the derivative is always the same given a different point x. So the derivative function is always going to be at least the same function, although the derivative value changes at a particular point of x. But you can use this then, once you've found what the derivative function is, to find the derivative or the slope at any given point that you want. Let's do another one. So again, I want you to use the definition of a derivative to find the derivative, and then we'll kind of use that for something else. So let's set up that first. So our derivative definition, or by definition, again, is the limit at h approaches 0 of f of x plus h minus f of x over h. Our function, a little bit more complicated, but pretty much the same as before. If I take my function here and evaluate at x plus h, I evaluate, or replace x with all of those pieces. So I'd have x plus h quantity squared plus x plus h. So that's my function evaluated at x plus h minus my function, which is x squared plus x, all over h. And again, I have a problem because I can't actually evaluate at h equals 0. I get a divide by 0 error, so I'm going to simplify the top a little bit. Same thing as before, we expanded that out. So I would end up with x squared plus 2xh plus h squared plus x plus h, minus x squared minus x. Forgot my parentheses there at first. Be careful, we're subtracting the entire quantity, x plus h, or f of x, which is x squared plus x, so we should distribute that negative through. The last thing that we did in our problem is then we simplified a little bit. We saw what canceled, and this will always happen. It's a good check for yourself. You should always end up canceling things out so that you'll end up being able to factor out that h, how we simplified the top that we did, or the numerator and the denominator last problem. That will always happen, so make sure that that happens in your case when you're dealing with polynomials especially. It's a good check for yourself that you actually did evaluate right. And what we have here at the end is 2xh plus h squared plus h all over h. And here's the point again, that we have an h in every term in the numerator, an h in the denominator. We can't evaluate yet, but we can simplify this to get that denominator divide by 0 error out of there. So we get x, or 2x plus h, and then plus 1 if we factored that out. Now there's a point when we're dealing with the limit that we can now evaluate at h equals 0, and when we do that, this h will go away and we'll be left with 2x plus 1. So if you do know shortcut rules, if you do know the power rule, you do know that these things are, or this function here, 2x plus 1, does in fact come from the power rule. So that's one way, again, to check yourself when you're doing definitions of a derivative. So our derivative function is 2x plus 1. And that means that I can use that derivative function to answer any question. So if I was asking you, what's the derivative at 1? What's the derivative at 100? What's the derivative at 1,000? We should be able to answer all those questions using this derivative function. Now, we won't actually do that for those ones, but again, that's why this thing is so powerful, is that we can find how this curve is changing, this curve x squared plus x, how it's changing at any given point once we have the derivative function found. Okay, last one for today. Is looking at x to the 5th. Now again, we're going to start with the definition of the derivative, and we're going to use that to find the derivative. I won't rewrite it out, but it looks like this again. So we're replacing our function, we're evaluating at x plus h. So our derivative here would be, again, the limit as h approaches 0 of x plus h to the 5th minus x to the 5th all over h. Okay, again, we have a divide by zero error. We can't actually evaluate at this point, so our next thing that we did is we expanded. So take a minute and expand this thing. Just kidding, I'm not going to make you expand that. There's actually a simple way to do that if you remember your expansion from Algebra 2, maybe pre-calc, when you talked about binomial expansion. So we can expand this pretty easily if we know a trick. And so one of the tricks that you can kind of have in your back pocket if you were expanding it, not that you necessarily need to know it, but it does come up in a homework problem, so I wanted to show it to you now, is you can use Pascal's triangle to come up with the coefficients in the binomial expansion. So I'm going to do that off to the side. So Pascal's triangle is derived from having, again, it's the coefficients of the binomial expansion. It has ones all down the sides of the triangle, and the numbers that are generated on the inside are from the addition of the two numbers above it. So this would be our n equals 1, this is n equals 2, our next one is n equals 0, n equals 1. This would be our n equals 2 row. So we always, again, start with 1, end with 1, and this middle term is taken by adding those two terms together to get our middle term. So our next row would be, again, 1, 1 and 2 is 3, 2 and 1 is 3, and 1. Our next row would be 1, 1 and 3 is 4, 3 and 3 is 6, 4, 1, 1, 5, 10, 10, 5, 1.
Hello everyone, just wanted to let you know the water.
And this, again, we could keep going on and on forever, but this helps us get to our binomial expansion of any two terms that we have. So, for example, this row, the 1, 2, 1, this would be the coefficients for the binomial expansion of x plus h squared. So how that worked is that our first term gives us our degree for our x squared term, and then every term that we go over, our x squared term goes down 1 in degree, and our h term, whatever this would be, goes up 1 term. And this is the coefficient that we have in front of it. So we start with x squared, 1x squared in fact, and this is 2 for our coefficient. The x power goes down, our h power goes up, so that we always have a degree of 2. So this is a degree of 2 with x squared, this is a degree of 2 of x to the 1, h to the 1. And then our last term again, h power goes down 1, or sorry, x power goes down 1, h power goes up 1, so this would be 1h squared. So this one, same thing, this would be like x cubed plus 3x squared h plus 3x h squared plus h cubed. And we can keep going. So this is the one that we're looking for because it's x to the 5th. So we'd start with x to the 5th, 1x to the 5th plus 5. Our x term goes down 1, so x to the 4th times h, so we always have a constant degree of 5, plus 10x cubed h squared plus 10 h squared h cubed plus 5x h to the 4th plus h to the 5th, and then I ran out of room, but then we also have that minus x to the 5th from our top here all over h. So again, I told you when you're doing these, at least with polynomials, you always should have something that cancels. So our x to the 5th term does in fact cancel with that last term that we had for this minus x to the 5th. And so we should be left then with every power here that has some h in it. And we do. So we could factor out an h and cancel it with this denominator. And if I do that and rewrite that so we can see that a little bit easier, we should have 5x to the 4th plus 10x cubed times h plus 10x squared, h squared plus 5x h cubed plus h to the 4th. And now we don't have that divided by 0 error in there, so we can evaluate at h equals 0, and when we do that, all of these last 4 terms will end up being 0, and we'll just be left with our first term, which is 5x to the 4th. So that's our derivative function for that problem. It would be 5 times whatever x value that you want to evaluate the curve, the slope of the curve at that given point of x. And again, if you do know power rule, you can kind of check yourself and see that that actually is correct.